Okay, so good morning and happy Wednesday to everyone. So today we would like to discuss altogether the applications of the Gauss elimination method and look at one more application, the so-called LU factorization. Okay, you will see that there are some very interesting things going on here. So I would like to actually get started with this one and then talk about everything else afterwards. So before I do so, are there any questions, please? So any questions on hints about the homework? Later today, I'm going to talk to you a lot about, in detail about the exam. Yeah, okay, so there is a request about exercise number 1. So let me look at number 1. Let me go there real quick. So for number 1, we actually did it in class. Okay, again, it's in the recording. I did an example in the recording of how you find the polynomial of a matrix. I actually solved it all the way. Okay, so we said that you simply, if somebody gives you something like, that's why it's important to review everything that we do. So if you have a question about grades, no, everything you discuss grades with me. So if you have something like this and you want to compute P of A, then P of A is simply going to be 3A squared plus 2I. It depends on whether it's A is 2 by 2. So if A happens to be 2 by 2, it will look like this. And I have solved a complete example in the previous class. It's in the recording. Okay. Yeah, so the question was, what's the difference between row echelon and reduced row echelon? And again, let me emphasize that here, I'm asking from the row echelon form that you you make the pivotal equal to 1, which is not necessarily what you're going to find in every book. So when I say row echelon form, I expect something like this. So this is row echelon, right? Why isn't it reduced row echelon? Can anybody tell me? So this is row echelon Y. In every row, the leftmost entry is 1, unless it consists all of zeros. And rows that are lower than others have their pivotal elements, the leftmost one elements on the right of the higher ones. And everything below every pivotal element is 0, right? So this is row echelon form. I claim that this is not reduced row echelon. Can anybody tell me which entry prevents this from being reduced row echelon form?
2.
Exactly. Very good. So it's the number 2. So what is the extra requirement from reduced row echelon form? Remember, I just said that for row echelon form, everything below every pivotal element. And what are the pivotal elements here? The pivotal elements are this one and this one. Pivotal elements are leftmost entries, leftmost non-zero entries that are equal to 1 in each row. So these pivotal elements are or we have to ask the question, is everything above the pivotal element 0? And you can see here that the answer is no. So this is not reduced row echelon. What would have been reduced row echelon form here? And this would have been reduced row echelon. So if you had something like 1, 3, 0, 0, 0, 1, 0, 0, 0. I never said that 2 is pivotal. 2 is not pivotal. 2 is an entry which is above a pivotal. So I said in reduced row echelon form, not only the entries that are below the pivotal should be 0, also the ones that are above the pivotal should be 0. Okay, that's what happens with reduced row echelon form. Okay. If a column doesn't have a pivotal element, there's no requirement about it. You cannot make them 0. Okay, that's why you can see here that nobody's saying anything about this number. This was a very good question. So look at this. Nobody says anything about this number. This number cannot be made equal to 0. Why? Because this whole column doesn't have a pivotal element. It doesn't have a pivotal element. You can eliminate things, entries, when you have a pivotal element on the same column. Remember how we find the column that doesn't have pivotal elements? We after we're done working with every column on the left of that, we look at the portion that leaves behind all the rows and all the columns that we have had. So for example, here, you would be looking at this portion. And when you look at this portion, you can see that this column right here doesn't have a non-zero element. So you cannot create a pivotal element. Okay, it's as simple as that. I remind you that you always leave behind you one row, one column every time you do an elimination on a column, right? So then you move on to the next column, and if you do not have a non-zero entry on that column, then you cannot make a pivotal element. Yes and no. I mean, look, the question is, or maybe I should rephrase the question by saying, are there advantages of reduced row echelon form compared to reduced to row echelon form? And the answer is yes. The matrix is going to be much simpler. Now, are there people that are going to solve the system by bringing it to reduced row echelon form? Sure. I personally don't like to do that, because I think it's fairly simple to solve the system once you bring it to row echelon form. That's why, so far, if you look at the things that we have done, I ask you to do reduced row echelon form only once. And what was that? When you find the inverse of a matrix. Okay, so so if for some reason you feel more comfortable, you feel strongly about reduced row echelon form, you like reduced row echelon form, right? If that's the case, nobody can stop you from doing reduced row echelon form. It's not a mistake. Okay, one of you can say, you know what, when I solve a system, when I extract a basis from generators, I want to do a reduced row echelon form. I just love reduced row echelon form. It's not a mistake. It's a personal taste, right? And I would like to emphasize this, that I have chosen to ask you to do the least amount of steps with the Gauss elimination method. That's my choice here. Could we have done everything by requiring to have a reduced row echelon form? The answer is absolutely. Absolutely. Well, yeah, you see, that's the point. The point is that once you go from row echelon form to reduced row echelon form, the pivotals do not change. So at least in the case of finding a basis, it seems completely unjustified to go to reduced row echelon form. That's again my personal opinion. Okay, the pivotals are not going to change. What you want to do is set columns with the coordinates of the vectors, do a Gauss elimination to bring it to row echelon form, and then choose the columns that have pivotals. That's it. That's how it works. Can you tell me why you would also do reduced row echelon form if you can already see what your pivotals are? Okay. There's no reason. The answer is there is no reason. Okay. Okay. Very good. And any more questions, please? Any more questions? Today, let me remind myself to actually explain to you why the method, this strange method that I showed you last time about finding the inverse works. So I would like to show you why this works. Okay, we gave it, it looks like magic, it finds what we want to find. Now let's try to explain why it works. Okay. Are there any more questions, please? So let me proceed with the LU factorization. So in many cases, I mean, as a general philosophy, the simpler a matrix is, the easier it is to use. So among square matrices, what are the simplest ones? So the simplest by far are the so-called diagonal matrices. So here's an example of a diagonal matrix. All of diagonal entries are 0. So this is a diagonal matrix. Diagonal matrix. All of diagonal entries are 0. Then we have the upper triangular matrix. Like this one, where, so this is upper triangular. All the entries below the main diagonal are 0. So what's the definition of an upper triangular matrix? All entries below the main diagonal. The main diagonal is always the diagonal that goes from the left upper corner to the right lower corner. All entries below the main diagonal and I repeat, the main diagonal is from upper left to lower right. Exactly. Every diagonal matrix is automatically upper triangular. And as you may guess, I'm going to also define lower triangular. So what is a lower triangular matrix? So a lower triangular matrix so this is lower triangular. And all the entries above the upper main diagonal have to be 0. Not below the main diagonal, the entries below the main diagonal. So all entries below the main diagonal, the ones that I put in the triangle, have to be equal to 0. Okay. And it is true that products of upper triangular matrices are upper triangular and products of lower triangular matrices are lower triangular, and products of diagonal matrices are diagonal. In fact, a matrix is diagonal if and only if it is both upper triangular and lower triangular at the same time. So, okay. Now, the next thing that I would like to show you today, which is an enormously useful thing, is that row operations are implemented by multiplying on the left by special matrices. So here's my thesis for today. Row operations are implemented by multiplying on the left by spatial matrices that are called elementary matrices. Okay, so let me show you how. So imagine that you have this matrix, right? And you want to perform the following row operation. You want to eliminate that -5, and you want to do 5 row 1 plus row 3. Let's say that you want to perform this row operation, right? I'm going to show you that you can choose your matrix. You can choose a matrix so that if you multiply on the left by that matrix, then that multiplication implements the row operation for you. Okay, and here's the matrix. So pretty much you take a matrix, which is the diagonal matrix, and then it has a non-zero entry at the right place. And we want to be able to add the 5 times the first row to the last row, right? So I claim that that matrix is going to have a 5 right here. And let's see how it works. Okay, so if I take this matrix and I multiply it, if I take my original matrix and I multiply by this matrix that I call E, do you see what will happen? So the first row has 1, 0, 0. So when you multiply it by each of the columns, what are you going to get? You're going to simply get the first entry. So this is going to change nothing. So it's going to give you 1, 2, 3. Then what will happen when you multiply the second row by each of the columns? Take a look at it. So when you multiply 0, 1, 0 by 1, 3, 5, the only thing that survives here is the number 3. Okay, so you're going to get 3, -1, 2. So nothing changes there. And now the really nice thing is what happens when you multiply 5, 0, 1 by 1, 3, -5. When you do that, then what you get is 5 times 1 plus -5, which gives you 0. 5 times 2 plus 6, so 10 plus 6, which is 16. And 5 times 3, which is 15, plus 4, which is 19. And that's it. Like I said, you have to choose one of the positions below the main diagonal and simply use that. You can just experiment, or here, I mean, you can see that the change has to occur when you produce the last row. So where do you put the 5? You put the 5 strategically in the first column. So this way, when you multiply this row and this column, like this, what happens? You get the 5 times 1, and then you add this to -5, which is multiplied by 1, but that's the same thing, right? That's the idea. So just to make sure that we clarify this, can you produce the matrix that will do -2 row 1 plus row 2? And then if you're done with that, produce the matrix that will do -3 row 2 plus row 3. Can you please do these two elementary matrices? Can you guess what they're going to be? So as I said before, they're going to have only one of diagonal non-zero entry. And it's going to be on the lower side of the matrix, so below the main diagonal. You just have to guess where it's going to be, and I don't think it's that hard to guess it. Give it a try by trying to anticipate the multiplication. Okay, let's see if you did it right. So here, the -2 row 1 plus row 2, and then the -3 row 2 plus row 3. I want you to do both of them. And these are really the only ones that we're going to use. We're producing, look at what is written on the top. We're producing a matrix so that if we multiply our given matrix with that matrix on the left, then we implement the corresponding row operation. So in the example that we did, by multiplying by E, we implemented 5 row 1 plus row 3. Okay. So here, for example, you're going to have 1, 1, 1, 0, 0, 0 for sure. Can you tell me where you're going to put that -2? You will have to place a -2. Can anybody tell me where to put it? In which entry? What row, what column? Second row, right. There's not too many things left on the second row, so it's going to be right here. No, E is the matrix that we're finding. When that matrix multiplies any other 3 by 3 matrix, it implements the corresponding row operation. And here, the matrix is, what is it going to be? Where do I put the -3? Third row, I have 2 places on the third row. Which one? Second place, very good. And you can try it. So take this matrix. I think what would be very instructive is to do this with a generic matrix that doesn't have numbers, that has, let's say, A1, A2, A3, B1, B2, B3. You can see very easily now what happens here. let's do it together. So sorry, this should be 1. Ask yourselves, first of all, what do you expect to get when you implement this operation? And the answer is you expect to get the third row should be replaced by negative 3b1 plus c1, negative 3b2 plus c2, negative 3b3 plus c3, right? That's what this operation is all about. So let's see what happens when we multiply these matrices. So multiply the first row by each of the columns of the second matrix, and you will simply get A1, A2, A3, right?
Excuse me.
Yes.
So, for example, if it was negative 3 row 1 plus row 3, so the negative 3 will be on the row 3 on the first place.
Yeah, we already, that's why I gave you examples of all the possible situations right here, so that you can see them. So we, by doing these 3 matrices, I really gave you examples of everything that we will need in our work for today, because I'm not going to ask you to do a 4 by 4. Basically, the examples are going to be 3 by 3. So you see where you need to place them. But like I said, I prefer if you actually did it on trial and error and see by what I'm doing right now that you produce the right result. So here on the second row, you will get B1, B2, B3 because you're multiplying by 0, 1, 0. And then on the last row, you're going to get what? Now think about it carefully. It's going to be minus 3B2 plus minus 3B1, I'm sorry, plus C1. And then minus 3B2 plus C2. And then minus 3B3 plus C3. And that's your matrix. Okay. Questions? Now, how about right? So what we're saying is that I'm not asking you from now on to be doing it this way, but this is going to be helpful for the LU factorization that we're going to explain. So we're not going all of a sudden to change everything that we have said so far about how we do their operations and start multiplying by matrices. All I'm saying is that all row operations can be implemented by multiplying by appropriately chosen matrices. Yeah, that's all I'm saying. And today we're going to use this fact. So what other row operations do we have? We have 2 more kinds of row operations. So let's say, how do you implement, let's say, row 1 with row 3? How do you swap 2 rows? And the answer is you will need to pretty much swap the rows, row 1 and row 3 in the identity matrix. So you're going to leave row 2 where it is, and then you're going to bring this over here and this over here. Okay, I claim that this matrix implements this row operation. And again, seeing is believing. So let's apply this to a generic matrix. So A1, A2, A3, B1, B2, B3, C1, C2, C3. And you're going to get 0, 0, 1 times each of the columns is going to give you what? C1, C2, C3 on the top. Then 0, 1, 0 times each of the columns is going to give you B1, B2, B3 on the second row. And finally, 1, 0, 0 times each of the columns will give you A1, A2, A3. And that's how we implemented our operation. So this is by far the simplest one. And finally, I have to show you how to implement 5 row 3, for example. Again, this is really very, very simple, possibly even simpler than the previous one. What you do is you put the diagonal matrix, the identity, and you replace the 1 corresponding to the row that you want to change to the number that you are multiplying by, which is 5. And that's it. Again, see how it works. If you do 1, 0, 0, 0, 1, 0, 0, 0, 5, then times A1, A2, A3, B1, B2, B3, C1, C2, C3, then what we get is A1, A2, A3, B1, B2, B3, none of this changes, and then finally you will get 5C1, 5C2, 5C3. So this tells you that all row operations are implemented in this very, very nice way. And you know what, we haven't used any column operations, but there are column operations, and column operations are also implemented by using multiplication on the right this time, not on the left. Okay, but we haven't used any column operations. Right, so if you want to swap, let's say row 2 with row 3, then you flip the second row with the third row on the identity matrix. That's what you do. Actually, matrices that have only one entry equal to 1 in each row and each column have a special name. They're called permutation matrices. So this is an example of a permutation matrix. They're very, very interesting matrices. Permutation matrix. It's a very interesting fact that they're exactly, can anybody guess how many permutation matrices there are? How many n by n permutation matrices? How many n by n permutation matrices are there? Again, I'm saying a matrix is called a permutation matrix if it has just one number, 1 on each row and each column, and everything else is 0. So can anybody guess how many n by n permutation matrices are there? Any guesses? So how many 3 by 3 permutation matrices can you make? You think 3. I don't think so. There are more. 3 by 3, there are more than 3 by 3 permutation matrices. There are?
N squared?
No, it's not n squared. That's a good guess. It's actually much larger than n squared. It's much
N
larger.
factorial?
Yes, that's the answer. N factorial. The answer is n factorial. So there are n factorial different n by n permutation matrices. Okay, now, the other thing that I would like to tell you is that finding the inverses of such matrices is the easiest thing in the world. Because all you need to imagine is what is the row operation that undoes what the row operation that I did. So, for example, if you have an elementary matrix like the ones that I showed you in the very beginning that have the 1 on 0 diagonal entry, like this one, can anybody guess what is the inverse of this matrix? What is the inverse of this matrix? Can anybody guess what it's going to be? It's very easy to describe it. Think about it this way. What operation undoes -4 row 1 plus row 2, which is exactly what this matrix implements? So what is the row operation that will undo -4 row 1 plus row 2? I'm sorry, 4 row 1 plus row 2. What is the one that... Oh boy. Okay, you will see why I'm laughing. So what undoes 4 row 1 plus row 2? No. Yeah, yes, -4 1 plus row 2, not minus row 2. So the one that undoes it is -4. So the inverse matrix is going to be simply this. So you just take the opposite of the off diagonal entry. So that's how you find the inverse matrix of such an elementary matrix. For the other ones, for the for the swap, can you guess what the inverse matrix is going to be there? This is even easier than. So if you swap row 1 and row 3, what is the row operation that undoes that? What row operation undoes what row 1 swapped with row 3 does? So we said that this is undone by -4 R1 plus row 2, which justifies why this will be the inverse. Row 1 swapped by row 3 is undone by what? Yeah, exactly. So it's the same thing pretty much. Row 1 by row 3. So guess what? All of these matrices have as inverse themselves. Not every permutation matrix, but these matrices that just flip a row. And finally, can anybody tell me if I have this? What is the inverse of this? What is the inverse of this? So 3 row 2 is undone by what? Exactly, 1/3 row 2. So the inverse of this will be 1 0 0 0 1/3 0 and 0 0 1. This is true in general. So if you take any diagonal matrix, the only way that the diagonal matrix is invertible is if all the diagonal entries are non-zero. And if somebody tells you, okay, find the inverse of 3, 5, -1 of this diagonal matrix, if somebody tells you find the inverse of this, then it's going to be 1/3 0 0 0 1/5 0 0 0 -1. That's it. There's one last remark that I didn't make when we talked about inverse matrices, but here it is. If somebody asks you, what is the inverse of the product of two matrices? The answer is quite unexpected. Can anybody guess what the answer is here? What is the inverse of the product of two matrices? It's the product of the inverses, but in the opposite order. And you can see why, because if you multiply a b, you can't really multiply by a to the -1, b to the -1, because you cannot commute the two matrices, so that wouldn't work. Instead, if you have a b and you multiply it by b to the -1 times a to the -1, you see what will happen. The middle matrix will become the identity. Once it's the identity, we can skip it. And then the product of these two matrices is the identity. Okay, so that's an interesting thing to remember about inverse matrices. So with all these things, I think it's time for you to look at the LU factorization. So basically our goal is to write, so our goal here is to write a square matrix as a product of the form L times U, where L is lower triangular, and U is upper triangular. Okay, that's the goal of this operation. So how do we achieve this? The idea is very, very simple. We're going to perform row operations so as to make the matrix upper triangular. The row operations will be chosen so that they're implemented by lower triangular matrices. And so we will multiply. So you start with your matrix A, and you start multiplying it by elementary matrices, E1 into, let's say, E3, so that these are all lower triangular. Then you hope to make this upper triangular. Once you have made it upper triangular, as a product, this was just A, as a product, L times U. I'm sorry about my handwriting. So once you have written it this way, then you can have that A is E3, E2, E1 to the -1. So you multiply both sides by the inverse of that. And this is pretty much going to be your L. And from this property that I gave you, it will turn out that this is exactly E1 to the -1, E2 to the -1, E3 to the -1. So this will be the matrix L, and the matrix U would be whatever you get. That is the plan. This is how we're going to implement our factorization. Okay, why don't we take a 5-minute break, and then we're going to see an example when we come back. Okay, and think of any questions that you may have. Okay, so let's try to see how we implement an example like that. Again, we may have to do different things for different matrices, but I will try to keep things as simple as possible. And here's where you might not want to touch your pivotal elements or allow pivotal elements to be not equal to 1. So here's what I mean by that. Let me give you example. Find an LU factorization for 1, 3, -1, 2, 1, 1, 3, 2, -2. Okay, let's do this example. Most matrices in this context are going to be quite simple. So here's what we do. I'm going to perform operation by operation, one at a time this time. So I'm going to do it as follows. I'm going to say, so what do I target? First of all, let's make our targets. So I want to make this entry, and this entry 0. Okay, so this way it will become lower triangular, upper triangular, right? Are you with me? So how do I make the 2 on the second row equal to 0? I simply implement -2 row 1 plus row 2. And now I will write down the matrix that implements this according to what we discussed before. So this will be 1, 0, 0, -2, 1, 0, 0, 0, 1. That's the matrix that implements this operation. I just take note of it. I don't do anything with it yet. And then I perform the operation. So the operation will become 1. The operation will give us 1, 3, -1, 0, -5, 3, and then 3, 2, -3. Okay, do we all agree? So now let's make the entry 3 on the third row equal to 0. So this will be achieved by the operation -3 row 1 plus row 3. And how is this operation implemented? It's implemented by 1, 0, 0, 0, 1, 0, -3, 0, 1, as we discussed before. So what becomes of it? 1, 3, -1, 0, -5, 3, and then we get 0, -7, and this becomes 0. And it's not a problem that it becomes 0. I mean, you can have this kind of situation. Finally, I want to target that -7. So here, and you know what? Somebody might ask, shouldn't we make that -5 into 1? And this is where I'm telling you, okay, now you are going to see why this is not always this is only for your convenience. Because to make -7 into 0, you need to add 7 to it. So how do you make -5 into 7? You multiply by 7 over -5. So all you need to do is do 7 over -5. So -7/5 times row 2 plus row 3. And how is that implemented? It's implemented by 1, 0, 0, 0, 1, 0, 0, -7/5, 0. So this is 1, I'm sorry. So this is the only case. This is the only case where we may have worked with a pivotal which is not equal to 1, just to make our life easier and use one less operation. The target for this operation has been this. You want to make this equal to 0, sorry. Come on, right? This equal to 0. Okay, that's your target. Okay, that's why you multiply by -7/5, so that -5 becomes 7. And when you add it below, you get, so what do we get? We get 1, 3, -1, 0, -5, 3, 0, 0. And here you have to be careful. We get -21 over 5, -21 over 5. -21 over 5. Our upper triangular has been created. I mean, when you perform the operation, you were adding -3 times row 1 plus row 3. The question was, how come this thing becomes 0 right here? And the answer is, when you perform this row operation, what do you get? You get -3 times -1 added to -3. That gives you 0. I mean, you have to perform it carefully. Okay. And I think there was another question. Yeah, but multiplying the matrices by the elementary matrix or perform their operation is the same thing. Okay, that's what we said. We said that traditionally we're thinking that we just perform their operation, but we know that what we're really doing here is to multiply by the matrix on the left. Okay, so this is U. This is U. This is U. And what is L? According to what we described before, L is going to be E1 to the negative 1, E2 to the negative 1, E3 to the negative 1, which is 1, 0, 0, 2, 1, 0, 0, 0, 1 times 1, 0, 0, 0, 1, 0, 3, 0, 1 times 1, 0, 0. You see how I'm taking the opposites of all of diagonal entries. And when we take the product of these three, I will simply find 1, 0, 0, 2, 1, 0, 3, 7/5, 1. And this is L. So here's the conclusion of this whole story. The conclusion is that our original matrix, 1, 3, negative 1, 2, 1, 1, 3, 2, negative 2, is written as 1, 0, 0, 2, 1, 0, 3, 7/5, 1 times 1, 3, negative 1, 0, negative 5, 3, 0, 0, negative 21 over 5. And that's your LU factorization. This is lower triangular, this is upper triangular. That's exactly what we were looking for. That's it. Okay. Questions? Yeah, absolutely. So -7 fifths row 2 plus row 3 is implemented by means of this matrix, because you can, and I suggest that you try to do it concretely. So take this matrix, E3, and multiply on the left the matrix, the generic matrix A1, A2, A3, as I showed you before, as I showed you when I was doing this. Okay, or even better, when I was doing this. And you will see that exactly the second row is being added to the third upon being multiplied by -7/5. Okay. So we said the general principle that we said is that every row operation is implemented by a matrix on the left, by multiplying by a matrix on the left, and we determine what that matrix is. And we showed for these three row operations that we will literally need how to find the elementary matrix. So if you look back at what we did here, you see how you need to form the matrix in each of these cases. These are the three cases that you need to know. Okay, that's all. Any more questions, please? So in other words, and this is far more important than the LU factorization, what we learned today is that all row operations can be implemented by multiplying on the left by appropriate matrices. Correspondingly, every column operation can be implemented by multiplying on the right by appropriate matrices too. Any more questions, please? And yes, you know what, I'll try to give you examples where pretty much it's identical to this, and L will always be like this. So if you had multiplied first by 1, then by 2, then by 3, then it's going to be the product of the 3 in the opposite order. I'm saying opposite order because as you have your matrix A, first you multiply by 1, then you multiply by 2, and then you multiply by 3. So you would expect the order to go like this, but since you take the inverse, and when you take the inverse, the order changes, then you can tell that it's like that. Any more questions, please? I would suggest that you take this example that we did, and you have all the details, and do it a few times. Okay, 1, 2, 3 times. That's why I insist, take one example, go back to the recording, and redo the examples. I repeat, or if you take notes, you can just do them of your notes and use the recording in order to make sure that you get all the details right. Okay, that's always the best way to prepare yourselves for this course. Now, let me go back and tell you why, explain to you why this method that we said you juxtapose A by IN, and then you start doing row operations till you bring it to the form IN B, if this is possible, if possible. Nobody says that it will necessarily be possible, but if it is possible to bring it in this, then what appears on the right is the inverse of A. And there are more than one ways to explain this, but the way that I'm going to explain it now is the most conceptual one. So first of all, I should mention the following incredible thing, which is really amazing, that we have the so-called block multiplication. What does that mean? What is block multiplication? So let's say that you're multiplying a 4 by 4 matrix. So let's say that you're multiplying, sorry, let me. Let's say that you multiplied, so this is 4 by 4. Let's say that you multiplied by 4 by 2, right? What does a 4 by 2 matrix look like? It's 1, 7, 3, -2, 4, 1, 5, 6. So this is a 4 by 2 matrix, right? You can do the following amazing thing. You can actually think of this matrix as being a 2 by 2 matrix where the entries are not numbers, but they are themselves 2 by 2 matrices. We call usually those 2 by 2 matrices, we call them blocks. So these are called blocks. And please understand, this can be done arbitrarily, pretty much. I mean, I could have separated like this, or I could have done a 3 by 3 piece and then and 1 by 1. I mean, there are many different ways in which you can partition a matrix into block matrices. And then here I would make this into 2 by 2 matrices like that. Now, if I consider this under this new identification as a 2 by 2 matrix consisting of blocks, and this by as a 2x1 matrix and I multiply them as blocks. So what would that mean? That would mean, for example, that I multiply this matrix times that, and this matrix times this, and then I add them up. My claim is I'm going to get exactly the same thing as if I had executed the multiplication differently. And this is always true. I mean, so any block multiplication that makes sense in terms of the dimensions always will give you the same result. So let's say that I have two 3x3 matrices, right? And so I consider this partition. So this is a 2x2 block. This is a 2x1. This is a 1x2, and this is a 1x1, right? And I apply a similar partition to the other matrix. And the reason I want a similar partition is because I want the things to actually make sense. Because otherwise, if for example, I partitioned it in some other way, then I could not form the corresponding product. So let's see what will happen now if I take this matrix and I multiply it by this matrix, right? This is a 2x2 times another 2x2. What is it going to give me? A 2x2. And what happens if I take this matrix now and I multiply it by this matrix? So, oops, this one is not possible. That's exactly what I meant. This is a 2x1. Oops, so I'm sorry. What I'm trying to say here is not even possible. So this partition is not going to work. Let me see if I can save this by some other partition. No, I don't think I can save this example. Oh, no. I'm sorry. It's a row times column, right? This is totally savable. So what mistake did I make? I'm so sorry. You will be watching this video and you will be laughing at me. So, oops, I want yellow. It's row times column. So, so what do you do here? You take this and that. So what is this? It's a 2x1 times a 1x2. A 2x1 times a 2x2, a 1x2 gives me a 2x2. So when I do these multiplications, I get two 2x2 matrices that I can proceed to add together, and that will give me a 2x2 matrix, which is the right result. So yes, this block multiplication is again possible. Okay, and that's it. So every time that a block multiplication is possible, so I partition my matrices in blocks, I have two matrices and multiply them together is possible, I will always be getting the same result as if I routinely multiply the matrices. Why is that now important? Because when I have my matrix A, IN, I can consider it as a block matrix consisting of an n by n juxtaposed with another n by n. And then what I do is row operations. Yes, but today we said that row operations are represented by multiplying on the left by different matrices. And you could have, I mean, in order to bring it to row echelon form, to reduce row echelon form, you may have 20 row operations, I don't know, 30 or 100. Right? The bottom line is that you multiply with a matrix on the left so that eventually EA, so eventually you will get EA times E times IN, or let me call this B. The order, of course, matters. The order in which you multiply this is, of course matters. Yeah. So this, you manage to turn it into the identity matrix. But exactly because you turn it into the identity matrix, this means that B is equal to A to the negative 1. So what appears here is B. This becomes B, which is exactly the inverse matrix. That's what explains what we just did. There are other ways to explain it, but this is one way to explain why the method works. Okay. Any questions? Yeah. I mean, in most cases, you won't be able to multiply blocks. I mean, in most cases, you won't be able to multiply. So let's say that you have 3, 1, 2. And so this is a 3 by 3. And then you have a 3 by 2, which is 1, 4, 2, 3, 9, 5. And then you consider this block here, and then you consider this block here. Okay, you cannot multiply this. Okay, here you have a 2 by 2, and you're trying to multiply it by and 1 by 2, and that's not even possible. No, so for the quiz on Friday, I'm going to give you an LU factorization, and I stand by my by what I told you to just redo this example a few times. I think this example has all the ingredients that you need to know. You don't need to do. If you want another example, you don't need to look up YouTube. You can look up YouTube, of course, but if you want another example, just change the numbers and redo the example. Right? There are some very simple-minded things that you can do like that. Okay. Now, at this point, I would like to discuss a little the upcoming exam. The exam is a week from this Friday. If you're taking it with extended time, you have to register at the DRC. Please don't mention that it's an online exam, because you're going to take it physically there. You're going to have to go to the DRC and claim your extra time. If you open the study guide, so please go to Blackboard right now and open the study guide, under exam guides, and you will see that the study guide has 10 problems, right? So the first problem is a Gauss-Jordan elimination method to solve a system. The second problem is to find the matrix of a basis. I'm sorry, to find the matrix of a linear map. The third problem is to find a basis for the kernel of a linear map. The fourth problem is to find a basis for the image of a linear map. The fifth problem is to find the inverse of a matrix. The sixth problem is to find an LU factorization. The seventh problem is to compute a determinant. We haven't done that yet. We'll do it next time. The eighth problem is to use Kramer's rule. We haven't done that yet. The ninth problem is to find the rank of a matrix. We haven't done that yet either. Even though we could have done it, it's very easy. And the 10th problem is to find the null space and the nullity of a matrix. We will cover this material on Friday, Monday, and Wednesday. And pretty much your exam will consist of 10 problems. And each problem will be exactly of the kind that you have here. So for example, in problem number 10, I will ask you to find the null space and the nullity of a matrix. Okay, open notes. No, they're not open notes. I mean, that's why no, there's not going to be a review session. You have your recordings where we solve exactly the same problems. Okay. So and open notes. No, I want you to know the material. there's not going to be open notes. First of all, you have 10 problems in 1 hour. If you had notes next to you, there would be a drag on you. They would cause you trouble rather than help you, for starters. Secondly, open notes math exams, unless they're super difficult, no, you're not allowed to use any notes. I'm sorry. When did you hear this thing that we do exams with notes? I mean, yeah, you will use this link. Exams are not supposed to be with notes. Exams examine what we know. Unless an exam has super difficult problems, in which case the notes are not a factor, and certainly you don't want me to give you such an exam, then taking an exam without notes. I mean, you should tell me, no, we don't want notes for an exam, because otherwise, we are going to have, I don't know, theoretical questions. We're going to have things that are not included in the notes. Nobody should ever, you should never allow anyone to give you an exam with open notes when you're going to be copying the things that you have in your notes and just change the numbers. You should never do that. If I came here and told you, take this exam with open notes, and you ask me, but is it going to be simple problems, or are you going to give us very difficult problems? And I told you, no, it's going to be simple problems, similar to the ones that we do in class. You're going to have your notes. You're going to have your notes next to you. You're going to look at your notes, do the problems, no problem, right? You of course, you will need to study still so that you know what is what. But if I did that, at least if I were in your shoes, I would be asking for a refund. Okay, it's as simple as that for me. Because it's as if I'm telling you that you cannot learn the material. Okay, you are young people at your prime, you study, and you learn the material very well. That's how this works. And anybody that ever suggests that you can do less than that, you should be protesting. Of course, that's me. But what I'm suggesting is the study guide tells you what the structure of the exam is going to be. I will give you instructions for the exam on the session before, so don't worry about it right now. The study guide really tells you what the 10 topics that are going to be on the exam are going to be, and exactly how they're going to be phrased. Okay, so I'm telling you all that. So for example, I just told you that you're going to have a problem to find the basis of a kernel, a problem to find the basis of the image. Okay, by the way, I'm afraid I haven't taken the attendance yet. So for attendance, just give me, I did this in the morning, sorry to those of you who have already done that, 10 problems, yeah. 4 plus 6 times 7. So please give me the answer to how much is 4 plus 6 times 7. Okay. Send it to me. There's a joke with this because, hopefully nobody's going to do the addition first. Okay, somebody was joking in the morning and did the addition, and I said, okay, it doesn't matter. It's not going to, I'm not going to because actually he was joking. He did get it right, and then he, to joke around, he gave me also the wrong one. But anyhow, so let's go back to the exam. I want to make it so that each one of you next Friday has a very clear picture of what I want from you. Okay, and I want you to prepare yourselves very, very well so that you use minimal time for each problem, so you know what to do right away. I will see to it that all the problems are given in a very in a very convenient way, in a very convenient fashion. Okay. Any more questions, please? So my advice to you is, if there's something that you don't understand the way it has been explained here, before you jump to other sources, please come and see me during my office hours and let's discuss it together. Okay. Now I will have office hours in 10 minutes, but there was somebody once. Let me. Okay. Bye, everyone.